This video is all about the chi-squared tests. We're going to be looking at a few tests in this particular video. The first one is called the goodness of fit test. And that's all about looking at a population, taking a sample, and saying, does the distribution of the population, based on what we've got from our sample, fit what we expected the distribution to be? And I'll talk about that as we go. Then after the goodness of fit test, we'll look at a test for independence. That's all about when you have two survey questions, qualitative, and you want to find out, are the answers to the different survey questions, are they independent of each other or are they dependent? Okay, or sometimes it's not a survey question, sometimes it's an observation, and you're observing two different things. So then the final test we'll look at is called the test for homogeneity. And that's kind of similar to the goodness of fit test, where the goodness of fit test was saying we have a population and we want to say, does the population's distribution fit something we expected? With homogeneity, we're going to be saying we have two different populations, and do their distributions fit each other? Are they the same as each other? So that's what this particular chapter is all about. And the chi-squared distribution is the distribution that's going to help us find the p-value for the hypothesis test that we're looking for. So here is just some graphs of some chi-squared distributions. It's a little bit like the t-distribution. There's degrees of freedom, and for each degrees of freedom, there's a different graph. So notice if the degrees of freedom are pretty low, this is a very skewed right distribution. Whereas if it is a much higher degree of freedom, then it's not quite as skewed right. It's a little bit more normal looking. One of the things when you have a chi-squared distribution, squaring makes things positive. So it turns out when you look at the distribution of the chi-squared distribution, you get no negative numbers. There is no such thing as a left-tailed test for a chi-squared distribution because it just stops at 0. Instead, everything will be right-tailed. And the p-value is going to be the area to the right of whatever value you're looking at. So that's kind of the graph of the chi-squared distributions. So now let's take a look at what chi-squared is all about. And what it is about, it measures how far the observed counts from the sample are from the expected counts. So one of the things is, since we're counting how many people said this and how many people said that and how many people said the other thing, the survey question will usually be qualitative. And this is really the first time we've been able to figure out how to do a hypothesis test for qualitative data. And that's what we're going to be looking at. We're going to say, well, we have a qualitative data, but we can count how many times people said that word. And then we say, well, did they say it the same number of times that we expected them to say it? And if they did, then we say that, yeah, we don't have any evidence to show that it's different from what we expected. Okay, but if it's very far from what we expected, then we're going to say there is statistically significant evidence to conclude the distributions are different. So here's just a little bit of math. And the way you say how far something is you subtract. You subtract what you observe minus the expected. Squaring it helps make it positive. That's one thing. And I'm not going to get into the deep math, but there's more reasons also. And then it turns out you divide by the expected, and that's kind of what percent you're off. If you multiply by 100%, that's kind of the idea. Okay, and that is what the chi-squared distribution is it's the distribution of all these observed minus expected squared minus expected is the idea. And you want to say, what do we get? The one little thing that we need, and this is similar to what you've seen when you had a yes/no question, is you need greater than 5. In particular, the expected counts must be greater than 5. Otherwise, we can't run a chi-squared distribution. Typically, if you have a very large sample size, there's no problem. But if you don't, you got to worry about it. So that is one thing about the chi-square distribution, and that's kind of the sample size limitation. So the first type of chi-squared test we're going to be looking at is the chi-squared goodness of fit test. And what it does is it tests to see if a distribution fits a known or expected distribution. So you don't need any real assumptions at all, other than the one assumption or the one thing we always have to make sure of whenever you're collecting data, and that is you don't have bias. If you have bias, basically, statistics is useless. So we basically need to say that we had random sampling or sampling that was representative of the population. So here's what we use the goodness of fit for. We typically want to either see, is the distribution normal? Because that's our big distribution. And a lot of times we said, well, if we can assume it's a normal distribution, then we could do all kinds of great things, even with a small sample size. Okay, so we want to say, is it normal? Or maybe do we have evidence to show that it isn't? And then you got to be real careful about a small sample size. Another would be uniform. That's important too. So in other words, are the answers to the survey question, do they all have the same probability of happening? And we'll have some examples of that. Okay, or sometimes you say, is it the same as a larger population or a previous population? So you want to say, has the distribution changed from before? Or maybe you live in a small town and you want to find out if the distribution in your little town is different than what we know about all of America, for example. And that would be comparing it to a larger population where you might know about all of America, because that might be documented, but you don't know about your little area. So that's how we do a large population. It's how we compare to a large population. That's what the goodness of fit is all about, is does the distribution fit the expected distribution? So in terms of the goodness of fit, this is a hypothesis test. So whenever you have a hypothesis test, you can have an H naught, the null hypothesis, and it is the distribution fits the given distribution. Typically, you're going to have this distribution, like a normal distribution, and you're going to want to say the distribution of my favorite stuff is normal or is uniform, or maybe the distribution of today's economy is the same as it was last year. That would be a typical thing. If you know last year, but you don't know what today is and you only have a sample. And then H1 is always the opposite, basically, and that is the distribution does not fit the given distribution, and that is the alternative hypothesis. Notice the word distribution. That is absolutely necessary for H naught and H1 for the goodness of fit test. So here's an example. 63% of SLT, that stands for South Lake Tahoe, that's for my town, residents are white. 27% are Hispanic, and 10% are of other races. The table below shows the results of a study of 300 randomly selected LTCC students. Is the racial composition of LTCC students different from that of South Lake Tahoe? And LTCC is Lake Tahoe Community College, by the way. That's the college I teach at. And we have this table, and in the sample that we looked at, there were 180 whites, there were 85 Hispanics, and there were 35 of other races. So let's start out by writing out the null hypothesis. And that is the racial distribution. Notice the word distribution. the racial distribution at Lake Tahoe Community College is the same as it is in South Lake Tahoe. And H1 is the racial distribution at Lake Tahoe Community College is not the same as it is in South Lake Tahoe. So we want to test this hypothesis. Okay, and maybe with a level of significance of 5%, something like that, but that's up to us. And usually when you get in advanced statistics and you're doing chi-squared, 5% is typical, but basically you look at the p-value and see how strong the evidence is. So what we need to do is we need to find the expected counts. And here's what we do. We know that we surveyed 300 people. Okay, if Lake Tahoe Community College was the same as South Lake Tahoe in terms of distribution, then 63% of those 300 should be white. 63% of 300 is 189. And that's why I have 189 in the expected counts table for the second row and first white column, I guess. Similarly, 27% of 300 is 81. So that's my expected for Hispanics. And then we had 10% of 300 is 30, and that's my expected for the other races. So now that we have our observed and our expected, we have our H0, we have our H1, and we know that we want to use a goodness of fit test. Hopefully you're all used to this by now. We go to a calculator. So let's go do that. So here's the calculator, and we're towards the end of the course. So I'm going to scroll almost to the very bottom. And notice goodness of fit. I want to do a goodness of fit test, so I click on goodness of fit. And it asks, type in the values from the observed and expected set separated by commas. So I need to type in my observed. So I'm going to save the time and just kind of do that. And the same thing with the expected. All right, I typed in my data, my observed and my expected. And then it's very simple. I hit calculate. The test statistic is chi-squared, and that's about 1.459, etc. That's kind of the placement on that graph that we saw earlier. And then the p-value is 0.482, etc. Hopefully at this point, you know how to interpret that. The p-value is much bigger than any level of significance that you would ever use. 0.48 is large. When it's large, that means that you fail to reject and there's statistically insignificant evidence. So let's go back and interpret. Our conclusion is there is insufficient evidence to make a conclusion about whether or not the racial composition of all Lake Tahoe Community College students is different from that of South Lake Tahoe. And that's it. That's how we apply the goodness of fit test. Let's look at another example. And the example is, does it matter what season a person was born in when it comes to getting into UCLA, my alma mater? Of the 400 Bruins, UCLA is the Bruins, who were surveyed, 93 were born in the winter, 95 in the spring, 126 in the summer, and 87 in the fall. So notice this is a goodness of fit. And in particular, we want to say, does it matter what season they were born in? If it doesn't, then the proportions should all be the same. And when everything is the same, every probability is the same, that's uniform. So in particular, H0 is the distribution of seasons that Bruins were born in is uniform. Notice the word distribution and the word uniform because we're looking at, is it a uniform distribution or not? So in particular, H1 is the distribution of seasons that Bruins were born in is not uniform. There's our alternative hypothesis. So next, we need to write down the observed and the expected. So I made a table. We have winter, spring, summer, and fall. The observed were 93, 95, 126, and 87. And the expected is actually quite easy. If it's uniform, if we surveyed 400 Bruins, and there's 4 seasons, and they all have the same probability, then there should be 100 each. So our expected will be 100 for the winter, 100 for the spring, 100 for the summer, and 100 for the fall, because uniform is all the same. Or in other words, 25% for each of them. 25% of 400 is 100. And there's our expected. And once we have the observed and the expected, now we can go to our calculator. So here's the calculator again. And to save you some time, I typed in the observed and I typed in the expected, separated by commas. And I hit calculate. And there we have it. Chi-squared is about 9.19. And the p-value is 0.0268, etc., etc. So in particular, this p-value is pretty small. And if we use a 5% level significance, then 0.027-ish is less than 0.05. And when the p-value is less than the level of significance, you reject the null hypothesis. So now we can go back and state our conclusion. We can conclude there is statistically significant evidence to conclude that the distribution of seasons that Bruins were born in is not uniform. Basically, you just restate H1 after saying there is statistically significant evidence to conclude that. You just write down H1. And that's it. There's our conclusion for this goodness of fit test. Let's do one more goodness of fit test. So here we have 400 students were asked how many pairs of shoes they own. Their mean was 12.1 and the standard deviation was 5. Below gives a frequency table of the results. Is there evidence to suggest that the distribution is not normal? So this one feels a little different. It turns out it's not much different, but it feels a little different because the others were actually qualitative questions, right? What season were you born in? I was born in summer. That's not a number. Here we have numbers, but we've written down intervals, and we're looking to see which interval it's in. And you could look at this as interval A, B, C, or D, for example. So it's not quite qualitative, but we can kind of think of it that way. Now we need to figure out the expected. And the way to do with the expected is we look at these intervals. Notice 12.1 is the mean. The standard deviation was 5. If you go 12.1 plus 5, you get 17.1. This is not a coincidence. And if you do 12.1 minus 5, you get 7.1. Also not a coincidence. So what this one, 7.1 to 12.1 represents is one standard deviation below the mean to the mean. And 12.1 to 17.1, that's one standard deviation above the mean from the mean. And then these guys are the outsides, 0 to 7.1 and 17.1, greater than that. So now we just got to remember the empirical rule. And that, if you remember, works as follows. 68% of the data should be within one standard deviation of the mean. So the left-hand side should be half of that, and half of 68% is 34%. So our expected would be 34% for this kind of lower middle interval and 34% for the upper middle. And then 68% inside means 32% outside. So half of that, because the far left will be half of the 32, since the far left and the far right make up 32. Half of 32 is 16. So 16% far left, 16% far right. And I can use those percents to come up with my expected counts. So 16% of 400 is 64. So 64 here on the far left, and also 64 on the far right. And 34% of 400 is 136. So there's 136 on this middle left interval, and 136 for the middle right interval. Now that we have our observed and our expected, we can jump into the calculator and find our chi-squared test statistic and our p-value. So let's do that. So here's the goodness of fit calculator again, chi-squared goodness of fit calculator. And to save you some time, I typed in the observed and the expected, separated by commas, and I just hit calculate. And our chi-squared is 25.39, etc. There's our test statistic. And the p-value is really small, 0.00001 ... The p-value is tiny. That means there's very strong evidence to reject the null hypothesis. So now we're ready to state our conclusion. The conclusion is there is statistically significant, in fact, we could say very strong statistically significant evidence to conclude that the distribution of the number of shoes owned is not normal. So this is not a normal distribution. So that's all I have to say about goodness of fit test. Let's move on to the next type of chi-squared test, which is called the test for independence. And what the test for independence does is it's used to test if two variables are independent. And these variables are usually qualitative variables. So you have the answer to two survey questions, and you want to find out if you have knowledge of the first answer. Does that help you with the second or not? Or maybe it doesn't. Are they independent of each other? So that's what the test for independence is all about. And just like all of our chi-squared, you don't need any assumptions other than no bias. So make sure random sampling or at least a representative sample. H0, the null hypothesis, is that the two categories are independent. And the opposite of independent is dependent. So H1, the alternative hypothesis, is the two categories are dependent. That's all there is to it. So don't forget, H0 is about being independent. H1 is about being dependent. Don't get those two confused, because then you're actually saying the opposite, which you don't want to do. So here's an example. 1,000 Americans were asked their political affiliation and their level of education. Is there evidence to suggest that political affiliation and education level are dependent? So we have a table, and typically for a test for independence, there's going to be a table. Notice that both of the survey questions are qualitative. The first is, what is your political affiliation? And the second is, what was your level of education? And, my level of education was post-college grad, okay? And I'm a Democrat. Okay, yours might be, maybe you're a college grad and you're a Republican. I don't know. But the point is, they're words, but so these numbers are not the answer. No one said 209. What this means is that there were 209 people who were Republicans that their highest level of education was graduating from high school. So that's what these numbers mean. These are counts. These are not the answers to a survey question. These are the counts of how many people answered in these two categories. So now let's go and state the null and alternative hypotheses. So H naught, the null hypothesis, is political affiliation and education are independent. And H1 is political affiliation and education are dependent. And we want to test this hypothesis. So if we want to test the hypothesis, now there's no observed and expected that we have to worry about. Pretty much the way the calculator works is you just put in the table and it'll let you know. It'll give you your chi-squared and it'll give you the p-value. So let's go to the calculator. So here's the calculator menu, and we're going to scroll way down because we're towards the end of the class. And if you look, we have tests for independence, and that's what we want because that's what we're doing. We're doing a chi-squared test for independence. And I click on that, and it says enter in the observed and hit calculate. And the chi-squared test statistic and the p-value will be calculated for you. Okay, and we should leave everything else blank that we don't fill in. So to save you time, I did this, and I put in all the numbers. So I just got to scroll down now and hit calculate. And there we have it. The chi-squared test statistic, 29.338, etc. And the p-value is very small, 0.0000052, etc. Tiny, tiny p-value. Tiny p-value? Reject the null hypothesis and say that there's strong statistically significant evidence. So now let's write down our conclusion. The conclusion is there is statistically significant evidence, and you can say strong statistically significant evidence if you want to conclude that the political affiliation and level of education are dependent, because H1 is that they're dependent. So just like good as a fit, you write there is statistically significant evidence to conclude that, and then you just retype your alternative hypothesis. And that's how test for independence works. Let's do one more example. So here it is. A study was done to see if college major and housing type are dependent. What can be concluded at the 0.05 level of significance? And what we have is housing type on campus, living with your parents, or other. And then I looked at our college major. You could be a STEM major, maybe arts and humanities, or other. And here were the counts for each of these parts. So for example, 182 were STEM majors who live with their parents. So now it's time to write down the null and alternative hypotheses. The null hypothesis, H naught, is college major and housing type are independent. And H1 is college major and housing type are dependent. Because again, when you have a test for independence, independent is what H naught gives you, and dependent is what H1 gives you. So we have our table. We know we're doing a test for independence. So now we just have to go ahead and go to our calculator and put in the values. So here's the chi-squared test for independence calculator, same one we just used. And I saved you some time and I typed in the table and I just scroll down and I hit calculate. And look at this. Chi-squared is 7.589, etc. The p-value is about 0.1078, etc. So now we go ahead and we can state our conclusion. When you have a p-value of 0.1078 with a level of significance of 5%, well, 10% or 11% is greater than 5%. So that means that there is insufficient evidence or statistically insignificant evidence. So let's write down the conclusion. The conclusion is there is statistically insignificant evidence to conclude that college major and housing type are dependent. And that's all there is to it for test for independence. Just got to remember the language, and you got to remember when to use a test for independence. It's typically used when there are two qualitative survey questions, and you want to find out whether the answers to the survey questions are related or not, are independent or dependent. So now let's do the very last type of chi-squared test that we're going to do for this chapter, and that is a test for homogeneity. And what a test for homogeneity does is it tests to see if two unknown populations have the same distribution as each other. So you have usually two groups, maybe men and women, or maybe, I don't know, where I live, locals and tourists. And you want to see, well, are they the same? Do they have the same distribution of whatever you might be interested in? So the good news is H naught is that the two populations have the same distribution. And H1 is the two populations have different distributions. Notice again, just like good does it fit, the word distribution or distributions because we're looking at two different distributions. So always include the word distribution or distributions when you're doing good does it fit and when you're doing homogeneity. Whereas for a test for independence, you include the word independent or dependent. So let's take a look at an example. 200 statistics students were asked how much they agreed with the following two statements. My grade reflects the amount of work I have put into this course. That's the first statement. And the second is my learning reflects the amount of work I have put into this course. And we want to say, are the distributions of the answers the same or not? And the table shows the results of the survey. And here's the table. So the survey asked about grade reflecting work and learning reflecting work. And this is what's called a 4-point Likert scale. Strongly agree, agree, disagree, and strongly disagree. And here, for example, there were 41 students that disagreed with grade reflects work. Okay, and we have all the numbers for the rest of them. So this is a typical thing. You want to say, well, are they the same distribution or do they differ from each other? And that's what we're interested in. So what can be concluded at the 5% level of significance? So as you're used to, let's write down the null hypothesis. And that is the distributions of answers to the two questions are the same. And the alternative hypothesis is the distributions of answers to the two questions are not the same. They have different distributions. That's all there is to it. And once we have our H0 and H1, we got our table. Now we can do our test for homogeneity using our calculator. So here's the calculator. And I'm going to scroll down. We're really close to the end now. So over here is test for homogeneity. And I click on that. And it says enter the observed values for each of the two samples, A and B, and hit calculate. And the chi-squared test statistic and the p-value will be calculated for you. So I'm going to save you some time, and I'm just going to type them all in. So I just typed them all in really fast. And here we got our data from A, and here we have the data from B. Those are the answers to the survey questions. And I scroll down, and I hit calculate. And our chi-squared test statistic is about 5.479, etc. And our p-value is 0.14. Notice the p-value is large. So when the p-value is large, that means there is statistically insignificant evidence, or there is insufficient evidence. Let's state our conclusion. The conclusion is there is insufficient evidence to make a conclusion about whether the distribution of answers to the two questions are the same or not. Again, whenever you have insufficient evidence, basically you just find a very fancy way of saying, I really don't know anything. I don't know if they're the same. I don't know if they're not the same. I just don't know. And that's this fancy way of saying it. Let's look at one final example. And this is at the 5% level of significance. Can it be concluded that there is a difference in the distribution of majors for men and women? And we can imagine a survey question saying, what is your major? And what is your gender? So we have this, in this case, instead of STEM, I wrote math science, and then a bunch of others, English, humanities, business, and other. And we have men and women. So here's our table. We want to find out if there's a difference in the distribution of majors for these two populations. Whenever you want to find out if there's a difference in the distributions for two populations, that's a test for homogeneity. So let's state H naught. And H naught, the null hypothesis, is the distributions of majors are the same for men and women. H1 is the distributions of majors for men differs from the distribution of majors for women. So notice H naught is always about being the same distribution, and H1 is about the two distributions being different from each other. And again, once we know we need a test for homogeneity, and we have our table, we can jump to our calculator. So let's do that. So here's the calculator again. And this time, save you some time, I put in all the data for the men and for the women. And I just scroll down. And I hit calculate. And look at this. Our chi-squared is 29.2385, etc. And the p-value is tiny, 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 0.0000007-ish. So p-value is really small. So when the p-value is really small, there is statistically significant evidence. Let's state our conclusion. We can conclude that there is statistically significant evidence to conclude that the distribution of majors for men differs from the distribution of majors for women, because that's what H1 says. And that is the conclusion to this hypothesis test. One of the things we can't do is we can't say which of the majors differ by men and women. All we can say is there's a difference in the distributions. We can't get into details. To get into details, you need to take an advanced statistics class. But in elementary stats, we just talk about, are the distributions the same or are the distributions different? And really, we never say the distributions are the same. Do we not have evidence to show that they're the same? Or do we have evidence to show they're different? And that is how a test for homogeneity works. So we've now seen the chi-squared test for goodness of fit, the chi-squared test for independence, and the chi-squared test for homogeneity. And this really helps us deal with questions that involve qualitative data. That's all I have to say for the chi-squared tests. I hope this all made sense to you. If not, please ask me if I'm your instructor, or ask your instructor if you have a different instructor, and we will be happy to help you out. Thank you for watching this video.